Day 521 of doing a LeetCode problem every day until I get a job. All right, y'all, we're back again. Another day, another LeetCode problem where we're doing daily LeetCode problems. And today we have question number 778, swim in rising water. The difficulty level is hard, but don't worry because you already know we're going to keep the solution as simple and easy to understand as possible. But before we get started, y'all, don't forget to like, hype, subscribe, comment, and share. And if you need any new Apple AirPods, go ahead and check out that link in the description so you can get you some. Now let's see what the question says. You are given an n by n integer matrix grid where each value grid of I and j represents the elevation at points I and j. It starts raining and water gradually rises over time. At time t, the water level is t, meaning any cell with elevation less than equal to t is submerged or reachable. You can swim from a square to another four directionally adjacent square if and only if the elevation of both squares individually are at most t. You can swim infinite distances in zero time. Of course, you must stay within the boundaries of the grid during your swim. Return the minimum time until you can reach the bottom right square, n-1, n-1, if you start at the top left square, 0, 0. All right, y'all, so that may seem a little bit confusing. Let's go ahead and take a look at these examples just to make sure that we are doing this problem correctly. So in our example one, we have our input grid equals a 2D array of integers. First array 0, 2, second array 1, 3. As you can see, each one of these arrays represents a different row. So this right here is this top row, and this right here is this bottom row. The output is 3. Explanation says at time 0 you are in grid location 0, 0. You cannot go anywhere else because the four directionally adjacent neighbors have a higher elevation than t equals 0. You cannot reach point 1, 1 until time 3 when the depth of the water is 3. We can swim anywhere inside the grid. So let's break this down one step further, y'all, so y'all can understand what's going on. We're starting right here at 0, 0 with a time of 0. We cannot go here until time 1. We cannot go here until time 2. And we cannot go here until time 3. Now, we could take this path to get to 3, or we could take this path to get to 3. If we go this path, we have to wait till time 1. We have to wait 1 hour till we could go right here. Boom, now we're right here. Then we have to wait 2 more hours till 3 hours pass total to go right here. Boom. Similarly, we could go this way. We just have to wait 2 hours to go right here. And then we have to wait 1 more hour to get right here, 3. But either way, we're going to have to wait 3 hours to get to this 3, right? We could go this way and wait for the 3 hours, or we could wait 2 hours and go this way, then wait 1 more hour to go this way. Or we could go this way, wait 1 hour, and then wait 2 more hours to go this way. But either way, we have to wait 3 hours to get to this point 1, 1 right here. Now, just in case that didn't make sense, let's take a look at example 2, where example 2 it's a little bit easier to understand and it's a bigger grid. Now, in example 2, we have our 2D input array grid. This represents each row, so it's the same thing. This right here will be the top row. Boom. Then this right here would be second row. Boom. As you can see, 24, 23, 22, 21, 5, 24, 23, 22, 21, 5. Boom. Then this array right here would be this row. Then this would be this row. And then finally, this would be this row. Boom. Our output is 16. The explanation says the final root is shown. We need to wait until time 16 so that 0, 0 and 4, 4 are connected. So let's break this down one step further, right? So we want to find the minimum time until we can reach the bottom right. So right now we're starting here. We could wait 1 hour, then go this way, then wait 1 more hour, go here, then 1 more, then go here, then 1 more, then go here, 1 more, then go here. But then you see to go here, it's going to take 16 hours. But once we wait the 16 hours and we're able to go here, the rest is smooth sailing because everything else is less than 16. So as you can see, everything else decrements or is less than or equal to or not even equal to, everything is less than 16 or less than its neighboring cell, so we could go this way. However, we still have to wait 16 hours to get here. That's why the output is 16, because out of this whole path, 16 is the largest or the most amount of time we had to wait. We had to wait 16 hours. Then after 16 hours, we were able to maneuver freely along this path, but we still had to wait 16 hours to get here. Now, that's important to remember, because you might wonder, well, we could have just went like this then. We could have just went 0 and then 24, 12, but we would have had to wait 24 hours. If we would have took this path, we would have had to wait 23 hours. If we would have took this path, we would have had to wait 22 hours. And if we would have took this path, we would have had to wait 21 hours. All of these are more than 16, right? When we could just go this path, and at most we had to wait 16 hours, where everything else we would have to wait at most more than 16 hours. Similarly, if we took one of these paths, we would also have to wait more than 16 hours. Say we want to go just straight here. Say we want to go here, then just straight down. We would have to wait 20 hours, right? Because there's a 20-hour cell in this path that we would have to wait. So by coming this way, we are able to utilize the minimum amount of time with this 16, and that allows us to go this path. So I hope that makes sense to y'all. And now that we understand the question, let's get into the fun part, the actual solution. We'll be using Dijkstra's algorithm. So I hope you're excited about that. Now let's get into it. So the first thing we are going to want to do is we're going to want to import the Swift collections library, and this is going to help for the heap data structures. So we could just come outside this class right here, and we could just say import collections. Boom. Then we need to define a struct to represent each cell in the grid, and it conforms to comparable, so it can be ordered inside the min heap. So we're going to come underneath this. We're going to create a struct. We could call it cell colon. It's going to conform to comparable, so we'll say colon comparable. We'll open up the brackets, and we're going to say let time, comma R, comma C, colon. They're all going to be integers. So time will be the maximum elevation encountered so far. R will be equal to the row, and C will be the column. Then we need to define the comparison between two cells based on their time value. So we're going to come underneath this. We're going to say static static func less than, open up the parentheses, LHS colon cell, comma, RHS colon cell, and it's going to return a boolean. Then we're going to open up the brackets, and we're going to say return LHS dot time is less than RHS dot time. Boom. Now let's get into the class, right? This main class that we got. So hold on, sorry y'all. Boom. So the first thing we want to do is we want to get the grid dimensions. So n will be the number of rows and m will be the number of columns. So to do that, we're going to say let, open up the parentheses, n, comma, m. We're going to set that equal to, open up the parentheses, grid dot count, comma, grid square bracket 0 dot count. Boom. And once again, this is the number of rows, and this, or n will be the number of rows right here, and then m will be the number of columns right here. Boom. Sorry, y'all, and this square bracket should be outside the 0, not outside the count. Boom. Now we need to track the visited position so we don't revisit the same cell using a set, and we're going to use a set to do that of row column pairs. So we're going to declare a variable, call it visited, and we're going to set that equal to a set, open up the parentheses, square bracket 0, comma 0. Boom. Now we're going to create a min heap or priority queue to always process the lowest time cell first. So we come underneath this, declare a variable called variable called min heap, set that equal to a heap less than cell greater than, and put the parentheses outside like that. Boom. Then we'll come underneath this, sorry y'all, and we'll start from the top left cell, which is 0, 0, with the initial time, its elevation, and equal to its elevation value. So we're going to say min heap dot insert, open up the parentheses, cell, open up the parentheses again, time, colon, grid, square bracket 0, square bracket 0, comma, R, colon 0, comma, C, colon 0. Now we need to define the 4 possible movement directions down, up, right, and left. So we come underneath this, we can say let directions equal square bracket, open up the parentheses, 1, comma, 0. Come outside those parentheses. We're going to say comma, open up some more parentheses, -1, comma, 0. Come outside those parentheses. We're going to say comma, open up some more parentheses, 0, comma, 1. Come outside those parentheses, comma, open up some more parentheses, and say 0, comma, -1. Just like that. Now, while there are still some cells to explore, we need to come right here and handle that by saying while exclamation point min heap dot is empty. When that exclamation point means while min heap is not empty, we're going to open up the brackets and we're going to remove the cell with the smallest time or the lowest elevation path that we so far. So we're going to say let cell equal min heap dot remove min, put the parentheses. Then if we reach the bottom right cell, we're going to return the time. This represents the earliest time we can reach the destination. So we're going to say if cell dot r equals n minus 1, comma, cell dot c equals m minus 1, then we're going to open up the brackets and we're going to return cell dot time. Boom. Now we need to explore all 4 possible neighboring cells by coming right here underneath this if, and we'll say for, open up the parentheses, dr, comma, dc. Then we're going to come outside of the parentheses, say in directions. We're going to open up the bracket. Boom. We're going to say let, open up the parentheses, row, comma, calls, or row, comma, call. We're going to set that equal to, open up the parentheses, cell.r plus dr, comma, cell.c plus dc. Boom. Now we need to skip if the new cell is out of bounds or already visited. So we're going to say, we're going to come underneath this let. We're going to say if row is less than 0 or 2 vertical lines, call is less than 0 or 2 more vertical lines, row equals n or 2 more vertical lines, call equals m or 2 more vertical lines, visited dot contains, open up the parentheses, open up the square bracket, row, comma, call. Then we could just come outside these parentheses, open up some brackets and say continue. Boom, just like that. Then we come underneath this and mark the new cell is visited by saying visited dot insert, open up the parentheses, open up the square brackets, row, comma, call. Boom. Now we need to insert the new cell into the heap, and the time to reach it is the maximum of the current's path time and the cell's elevation. And since we must wait until the water rises high enough to reach the elevation. So we're going to come right here underneath this, and we're going to say min heap dot insert, open up the parentheses. We're going to say cell, open up some more parentheses, time, colon, max open up the parentheses, cell dot time, comma, grid, square bracket row, square bracket call, come outside these first parentheses right here, we're going to say comma R colon row, comma C colon call. Boom. Then finally, last but not least, if we somehow can't reach the end, and this shouldn't happen just because of the problem constraints, then we could just come right here and we could say return -1. Boom, y'all. That's all she wrote. Let's give it a run before we submit it. Make sure it runs correctly. It's accepted first try. That's what I'm talking about, y'all. So let's see if it's still accepted after we submit it. And look at that, y'all. 19 milliseconds beats 34.38% of users. Not bad. We can definitely get those numbers up, but I think this was a good solution to choose and learn from because it's easy to understand and it's easy to learn from, and we get to practice our understanding of Dijkstra's algorithm, which is always fun to learn new algorithms and how to improve our algorithm and data structure understanding as a whole. So y'all, with that being said, get one more look at the code. This is the top part. This right here is the middle, or actually this is the bottom. This is the rest of the code, y'all. So with that being said, I hope y'all learned something today, and I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.